Recording? Yes, I am. I'm going to do this a little backwards because I want my students who showed up to class to get a chance to look at this Monty Hall problem, which I mentioned but didn't really go into. It's really fun. It's actually mentioned in the reading, and there's kind of a place you can go look at it, which I'll post as well. But this is a very interesting problem that causes lots of controversy. There's this woman who's considered one of the smartest people in the world who used to write a column, and when she explained it, people were angry because they just thought she was wrong, and she wasn't wrong. People would just have a hard time understanding this. So here's the deal. Monty Hall used to be a game show, and the idea is you had 3 doors to pick behind. Behind 2 of them is a goat, and behind 1 of them is a car. And the way this works is you pick a door. So I'm going to just pick door 1. And then Monty's going to show you, hey, one of the 2 doors that you didn't pick, he's going to show the goat behind one of the doors you can pick. So if I picked 1, and so he's showing me that there's a goat behind this door. He will always show me where a goat is. The question is, should I switch doors? Okay. I'm going to let you play this to figure it out. I am going to switch doors. Oh, and I won. What a surprise. And so once again, you need to understand that Monty actually knows where the goat is, and he will always show you where the goat is behind one of the doors that you didn't pick. So does it matter if you switch or not? And I will reveal this at the very end of the video if you're willing to watch all the way through it. But you've got the setup and you have the link, so go play. For those people who weren't in class, quick little lesson. And I'm going to make a note to myself, reveal answer, because I'll forget. And I'll try to explain. We had this in our reading. It was a little thing about crayons. And the idea is you've got 8 crayons. Somebody comes by, they pick 1 out of the bag, they use it, put it back, and then another person comes by and gets a crayon. And the question is, that second person, what's the chance they got the yellow crayon? There's only 1 yellow crayon. There's 8 crayons, so standard box. Okay, my guess is most of you say, well, there's a 1 in 8 chance. There's 1 yellow crayon in 8, 1 in 8 chance. That's right. Okay, a person chooses a crayon out of the bag, walks off. Second person comes up, gets the crayon out of the bag. What's the probability the person gets the yellow crayon? Which the answer is what? That's right, 1 out of 7. Unless the first person got the yellow crayon, in which case the probability is 0 out of 7. So this is a really good example of what's called an independent event, because these 2 things, the crayon doesn't matter in this first case, and in the second case is what's called a dependent event, because it totally depends on what happens in the first case. And once again, this is all in the reading. You can go back and look at it. So normally, to calculate the probability of 2 events happening, we can just multiply the probability of A times the probability of B. So in our first warm-up, they didn't ask us this, but the probability of both people getting the yellow is 1/8 for the first person and 1/8 for the second person. And if I want to know the chance of both of them getting it, I multiply those together and I get 1 out of 64 or 1 over 64. And once again, this is an independent event. The crayon is put back, and this is often said with replacement. When you read probability problems, if they say with replacement, or it's obvious they're putting things back to the original sample space, that's called with replacement. And those are independent events. You can just say, okay, it's 1/8 and 1/8 or 1/8 or whatever the other things happens to be. That would be the possibility. The tricky part happens is if the B thing happens to be second, like there's some kind of order, and it's also affected by the outcome of A. So suddenly, like, oh wait, things have changed. And so for number 2, the odds of both people getting the yellow is calculated by, well, the chance of the first person getting yellow is 1/8. And then the possibility of the second person getting yellow is 0 out of 7, because 1 less thing's in the bag. And if the first person has already gotten that yellow one, there is no chance. Okay. So this is what's known as without replacement. So I'm not putting things back. This is called a dependent event. Basically, the crayon walks off. And one of the reasons it makes a difference is your sample space got smaller. this denominator number will always change when we're doing without replacement because I've taken one thing away. The top number may or may not change depending on whether or not that item was removed from the box or the bag or whatever we're doing. So I've got another example here. So I've got probability of 3 red marbles and 2 blue marbles. And once again, if you go back to the reading, you'll see one very similar to that. So the probability of red is just, 3 out of 5. Probability of blue is 2 out of 5. The probability of red then blue with replacement is just multiplying those two things together. Okay, it's 3/5 for the first one, and 2/5 for the second one, and that's going to give me a number of 6 out of 25 because my sample space is actually 25. There are 25 possible things that can happen. There are 5 different marbles I can draw the first time out of the bag. I put it back. There are 5 different marbles I can draw the second time. So there's 25 combinations of marbles. If every marble is essentially unique. And then there's 6 different ways that can happen of red then blue. Now, without a replacement, what's that going to be? Well, the first number doesn't change. Still 3/5. But the second number, if I've gotten a red already, what's the probability of me getting a blue now? Well, it's still 2, but it's not out of 5 anymore. It's 4. There's only 4 marbles in the bag. So this is going to be a different number. And the question, would this be more likely or less likely? It actually would be more likely because there's fewer marbles in the bag on the second try. So there's a slightly better chance. The 2/4 is a better chance than 2/5. So there's a slightly better chance that this will happen without replacement. So that would end up being 6/20. Okay, slightly better odds. And then I think I did one more in class. I said, what's the probability of red, blue, then blue? And that's without replacement. Okay, well, first one, blue in general is 2/5. Now, what's the chance? I pulled one blue out. What's the chance of me getting that second blue now that I've removed one? Right, it's going to be 1 out of 4. And this is very unlikely to happen because once I take the blue out, first of all, there's not a great chance I'm going to get the blue to begin with. But that second one, there's fewer blues in the bag now. So this is probably one of the least likely events in all of these kind of combinations. So that would be 2 out of 20. Okay. I want to do one more set of new problems. I've got some. This is something I didn't do in class, but it's similar to one that I did in class. So I've got numbers 1 through 8 on tiles that are put in a hat. Andre pulls one out, puts it back. Claire selects one at random. What's the probability of Andre selects a tile? Well, 1 in 8. This is almost identical to our warm-up. What's the probability? Claire selects a tile. Now, you've got to go back and make sure you're reading it. He replaces it. This has a completely different answer if he does not replace it, but he replaces it. So 1/8 again. What's the probability that both Andre and Claire select tile label 2? Well, it's 1/8 times 1/8. Okay. Are the events of Andre selecting a tile and Claire selecting a tile dependent or independent? They are independent events. I can make my mouse work. Okay. Because one doesn't affect the other. The second one does not depend on what happened in the first one. Okay, if Andre selects the first but does not put his tile back, what's the probability of Claire getting it too? We don't actually, well, we know the probability of her, it depends. We've got to know what happened with Andre. If he got it, the chance of her getting a 2 is 0 out of 7. Okay. If the probability, if he didn't get it, the probability is 1 out of 7. And notice this is not both of them happening. It's just saying he doesn't put it back. So this one totally depends. All right. I want to go back and actually let me undo some of this stuff. I want to go back and talk about Monty Hall before we go. So here's the deal. it always makes more sense to switch. And this is really counterintuitive to a lot of people because they think, play again. I'm gonna pick 3. So I'm gonna pick 3. Okay. Monty's gonna show me, oh, goat's behind the door. Monty knew it was. Think about it this way. A lot of people think, oh, wait, it doesn't matter. You got a 50% chance. You may as well just stick, but you don't have a 50% chance. You have a better chance than that. This is very, very counterintuitive, but think about it this way. You had a 1/3 chance of being right, but you had a 2/3 chance of being wrong. So it was very likely that you are wrong right now. Very likely that you're wrong. 2/3 chance that you are wrong because it's probably behind one of the O2 doors. Okay, as soon as he reveals that one, he's basically telling you you've got a better chance. I'm explaining it badly. He's basically saying, hey, you don't have to have a 2/3 chance anymore. You have a much lower chance. And if you actually looked down here, you will see that people who switched won about 2/3 of the time. This is experimental data, so it's not going to be exact. And the people who didn't switch only won about 40%. That's weird. Things don't add up. Anyway, and then there's another version you can play where he does not know, and you'll notice that it totally doesn't matter if you switch or not. So you might want to check that one out. Okay, that's enough. Thanks for watching.